Basically, you're taking the technology and capabilities, engineering capabilities, and exploring parameter space so you can identify all the tall poles in the tent in terms of the instrument. And mission design. What we're doing here is not just design reference mission. We're doing, in fact, a campaign, a design reference campaign. And the difference is that what we're trying to do is do an overarching view of destinations and a coordination so that individual design reference missions can be fit into a larger campaign, and it can be extremely synergistic. But why the moon? Well, obviously the moon we know a lot about. 6 lunar exploration expeditions to the moon. Incredible data came back from this, and it means that the moon is a cornerstone in terms of our understanding of other planetary bodies. We have 1 or more spacecraft currently or recently orbiting each of the terrestrial planets, and in fact we have really fundamental questions about the formation and evolution of all of these that the moon can be utilized as a basis to understand. In addition, we have had dozens and dozens of missions. Prior to Apollo, there were 21 U.S. robotic missions in preparations for Apollo. We had Apollo 6 successful expeditions, and numerous Soviet missions, about 40, okay? In addition to that, of course, in the last decade, we've had a renaissance. 2003 up to the future, it's been a real rebirth in lunar science, and there are 10 lunar missions flown in this period and many more to come. And there's going to be a deluge once X Prize starts flying, etc. So everything's changed but our way of thinking. We have a huge amount of new information, and we have really fundamental questions to address. So what I want to briefly describe is the importance of coordinated lunar and human and robotic exploration, and talk a little bit about why the Orientale Basin could be the best place for this. Let's start with the importance of coordination, okay? First of all, our concept here is to, in fact, work on a whole host of missions which are part of this broad-scale campaign architecture, but which individual countries can place their spacecraft capabilities within this to add to a coordinated whole. So we see precursor missions. What do we need to know before we send humans, for example? Context missions. What are the robotic mission requirements for final landing site selection and regional context for landing site results? Infrastructure and operations. We need to think about missions to fly, like a communications capability, complete communications capability for the near side and far side and beyond. Interpolation. How do we use robotic missions to interpolate between human traverses, for example, and extrapolation? Once we get the data, we know we want to go beyond where we are now in that area, so how do we use robotic missions to extrapolate beyond the human radius? And so if we take a look at this, this is a map which puts at a common center all the Apollo missions and the Lunicod missions and the Mars missions as well, placed over here. And you can see it out to a radius of about 14 kilometers, how much landscape was covered, in fact, by the Apollo missions. But let's take a look at Lunicod 2, extending all the way out to 14 kilometers, Lunicod 1 extending out to about 8 kilometers. And you can see from this that the complementarity of these human and robotic missions could be really, really important in all those areas that I identified. Furthermore, we can combine human and robotic together. I worked in the Apollo program and worked on Apollo 19 to 21, which none of you have ever heard of, but trust me, they were going to fly before some idiotic political decisions, can I say? Nonetheless, what was going on there was that once the Apollo mission had finished, okay, there was a rover that was connected to the back of the lunar rover that was sent off to the next landing site to traverse the area between the 2 landing sites to get interpolation and fill in the history of the moon. And then finally, progeny, what do we do to target successor missions past this? Let me mention why the Oriental multi-ring basin. This should be no news to anybody, so let me go through and just highlight the various places that this is important. First of all, we know from our previous discussions that the moon is, in fact, a laboratory for the study of primary and secondary crusts, okay? This is really important because we don't see this on the Earth, and they're different on other planetary bodies. And we've had a lot of SEED, survey-sponsored workshops, microsymposium, et cetera, in which we've identified the key questions that derive from this type of activity. And so it's really important. Secondly, so studying multi-ring basins is really a critical aspect to understanding the whole cratering history. What's the transition from peak rings to multi-ring basins and craters to peak ring basins? In addition, we know that the type area for lunar basin formation and evolution is the Lunar Oriental Basin. It's the youngest, it's the best preserved, and this just beautifully displays not just all the rings, but all the basin units, etc. They're there waiting for us to examine, and it's really important for us to get there and do a comprehensive study of this area. We can also try to understand where the transient cavity rim is. This is a big debated issue in planetary cratering and planetary basin formation. Which of these rings is it? Well, let's go take a look. We have questions that we can raise, and things we can do to make measurements. This is a basic cartoon about how the collapse phase of basin formation occurs. And in fact, you know, I never like to use the term cartoon, but this does represent a poor understanding of what is actually going on. We're getting new data, we're getting more data, but we really need to understand this, and clearly Orientale is the place to go. We have a lot of new data on topography, on gravity, and crustal thickness, and so we can use this as a roadmap to design this architecture to test these types of things. And in fact, we can go in and understand the characteristics and origin of the geological units. We have the ejecta, we have the impact melt inside the basin in this unusual unit, the Montes Rook Formation, which nobody is really sure what's going on, but the key, it is the key to basin collapse characteristics. We've used the MOLA data and other, that would be the LOLA data and other data to characterize the thickness, ejecta thickness decay, so we can kind of get an idea of what to expect at different radial traverses away from the basin, but we need to sample it. We also don't understand fully the vertical structure in the crust of the moon. We know that Orientale preserves and exposes a lot of that, so this is a good test for understanding the vertical structure and lateral changes in the crust of the moon, and we have a lot of guidance from the MQ mission for the kinds of features that we see there, and we actually have the capability in terms of going in and looking at individual massifs to see what the dominant mineralogy is, so we can go actually to these areas, target them, and get the data we need to address these fundamental questions. Orientale in the interior looks like it's an impact melt sea. I'll talk a little bit about that tomorrow, but the bottom line is there could be a 12-kilometer thick solidified impact melt sea here, whether it differentiated or not, and other major issues are really critical, and this is the place to go and address that question. And the mare-like Imbrium and the basins like Imbrium, it's covered up by kilometers of lava. And of course, we have links to the Apollo missions. This is really exciting. If you map out each of the individual Apollo missions, to the Oriental Basin, Apollo 17 landed at this type of ring, 15 landed at this type of ring in Hadley, and throughout this, out to Apollo 14 and 16, we have analogs here. So we can actually give rebirth to the analysis of the lunar samples from the Apollo missions by understanding them in this context. You can see this here. Here's Apollo 17, 16, 20, and Luna 20, 14, and 16. So these are really, really important. And furthermore, we have Maria in the basin. If you take a look here at this simulation, okay, 1 second, readjust your temporal lobes. That makes sense, yeah, your temporal lobes. Okay, 1 second is 100 million years, so we're going to go through this and take a look at the distribution of lavas from Jenny Witten's work. Okay, the basin forms at 3.7, 3.59 here, and you can just simply see the sequence of lavas that are coming in through here, and they're all available for examination. We're looking at the change of basaltic magma as a function of lunar history right there in the Oriental Basin. And there's a couple more here. I won't, well, there it is. All the way to 1.66 gigayears. And in fact, if we take a look at the near side Maria and look at the distribution of ages in the work of Harry Hiesinger, etc., the Oriental ages here are essentially the full range that we'd see on the near side. So we can actually look at that full range in the Oriental Basin. So let me just point out a couple of things here as I close to talk about the areas of interest, okay? Human robotic scientific destinations. We have 4 basic regions of interest that we're exploring. The first one here is the origin of the basin rings crustal structure. So this would be the region of interest is landing and having multiple missions into these areas here with the Cordillera and the outer Rook Ring of the Oriental Basin and the deposits in between. The second major area of interest, region of interest, is the origin of the inner Rook Mountains. Could these be peak rings from an impact basin, such as a peak ring basin? What's the transition? How do they change when they go to larger basin sizes like Oriental? And in fact, what is the mineralogy of these things? This is a critical aspect to understanding the origin of peak rings in the moon as a whole. And of course, region of interest 3 is the Oriental Melt Sea here, the impact melt sea. There's a little bit of Mare in here, but as you'll see in the next slide, the Mare actually doesn't cover up a significant part of the impact melt sheet, and we design one of our region of interest into this area here. And then finally, there's a very unusual Io-like, that would be the inner satellite of the Jovian system eruption here. It's a plume-like eruption that the vent is right here, and you can see here it is here, and you can see this over 100-kilometer diameter ring, which we think is a pyroclastic eruption. How did that occur? Why is it almost unique on the moon? It's related to the Oriental Basin. So these regions of interest illustrate what one could do in putting together an architecture which is a basis for a design reference mission. So just think about this, if you will. Think about the possibility of taking all this international input here, okay, and each individual nation can fly, based on their capabilities and their national interest, missions to the moon, but internationally, we could also put all this together to have a design reference architecture. So those particular countries could place, communications infrastructure into orbit around the moon. They could place rovers on the surface. If they're developing sample return robotic capabilities, they could, in fact, fit into this basic architecture for sending humans to the moon, as the Chinese will do by 2035, they say. Then, in fact, this could be a place that we could all get together and essentially accomplish some very, very significant goals. So we're looking at here human robotic exploration, design, reference architecture, and I hope we can all work towards the future in making something like this a reality. Thank you very much.
All right. Thank you, Jim. Once again, we're running a few minutes behind because of our late start, so I think we'll go with no questions for the moment. We want to make sure Tony has a chance to sprint over to the other room without too much overlap. And again, in the afternoon session after Dan's